So with what we've just written down, now we're ready to write down the definition of the limit. So we say that if you have a subset of the real line, a function with domain equal to that subset, and numbers p and l, then we say that the limit as x approaches p of f of x is equal to l if, for all epsilon bigger than 0, there exists a delta bigger than 0, such that for all x values in the domain, if 0 is less than the absolute value of x minus p is less than delta, then the absolute value of f of x minus l is less than epsilon. So what do you think? Does that look pretty similar to the definition of the limit of a sequence? And it should, right? It's trying to capture something very similar. Instead of capturing what happens when some variable n is close to infinity, we'll ask what happens when some variable x is close to p. And that's, so that means that a lot of proofs involving limits of functions should look similar to proofs involving limits of sequences. And let's see one. So you guys just told me, well, that the limit as x approaches 3 of 4x minus 2 should be equal to 10, did you say? Let's try to prove that. So that means we need to prove that for every epsilon bigger than 0, there exists a delta bigger than 0 such that for every x in the domain of this function, what's the domain of that function? All the real line. So u is going to be the real line for this one. For every real number, if 0 is less than the absolute value of x minus 3 is less than delta, then the absolute value of this function minus 10 is less than epsilon. That's what we need to show. So if that's what we need to show, we need to show something's true for every epsilon bigger than 0. So what should be the first line of our proof? Consider any epsilon bigger than 0. I think I'm going to switch colors again. Consider any epsilon bigger than 0. Next, I need to come up with a choice of delta. And just like how in epsilon n proofs, we just would write let n be equal to, and then we drew a blank and figured out what went there later. We'll do the same thing. Let delta be something that we'll figure out once we know what should go there. Does anyone already have some intuition about what delta might be? Okay. Epsilon over 4? Something like that might work. Let's find out if that works by trying to write a proof. Let delta be something. Next, we'll consider any x in the real line and assume 0 is less than the absolute value of x minus 3 is less than this variable for delta that we picked. Then we need to show something about the absolute value of this function for x minus 2 minus 10. All right, we need to show that that's less than epsilon. So let's just go through and see what happens. 4x minus 2 minus 10. Well, how does that simplify? Yeah, just say that out loud.
2x minus 1 minus x. Or is that one?
Yeah, they're both minus, right? So this will be like the same as, maybe that's what you said, 4x minus 12? What simplification could we do from here?
It's less than 4x. There's the value of 4x.
Is it though? Because that 12, like, what? How about if we factor out a 4? Let's try that. But wait, did we assume something about the absolute value of x minus 3? It's less than delta. So this whole thing is less than 4 delta. Okay. But we get to pick delta, right? We get to say what delta is equal to. Is there a choice of delta we could make so that that's equal to epsilon? Epsilon over 4. So let's make this choice delta equal to epsilon over 4. Then this will become 4 times epsilon over 4 by our choice of delta, which is just equal to epsilon. So let's just check if we've actually proven what we needed to. Did we start by considering any epsilon bigger than 0? Did we then come up with a choice of delta? Did we consider any x in the real numbers and assume that 0 is less than absolute value of x minus p is less than delta? And did we conclude that the absolute value of the function minus the alleged limit is less than epsilon? So, summarizing, for every epsilon bigger than 0, there exists a delta bigger than 0, such that if 0 is less than the absolute value of x minus 3 is less than delta, then the absolute value of f of x minus 10 is less than epsilon, meaning that the limit as x approaches 3 of 4x minus 2 is equal to 10. How do people feel about that? That go okay? Like maybe it was faster than you would have done it on your own time, but that's just because I only have 50 minutes. So let's take a look at this sort of definition. There's like an if-then statement there, right? So let's suppose that your domain is such that there are no x values within a delta of p other than p itself. Let's think about what that would mean for this epsilon delta definition. So if the if part of an if-then is false, what can you tell me about that if-then statement? Well, it's automatically true. Right? If the name of today ends in a Q, then today is fall. That's a true statement, because there is no day that ends in a Q. You get a vacuous if-then statement. So if you think about what that means, you could assign any value to be the limit as x approaches p of f of x if p isn't close to anything in the domain, which is like really dumb, right? That would just be a bad definition of the limit. So you should only take limits at points where that if-then is satisfied, where the the hypothesis in that if-then isn't vacuous. So let's write down what that means. So if I give you a subset U and a point P in her, then that point P is called an accumulation point of view, or a limit point of view. Which of the people here took topology last semester? Oh, just you. I thought there was more people. Okay. Well, then you already know what I'm going to try. A point is a limit point of a subset if for every delta bigger than 0, there exists some x in U such that absolute value of x minus 0 is less than the absolute value of x minus p is less than delta. And let's maybe just draw a picture of what that means. No, let's write in words what that means. So what does that mean? That means no matter how close to p you look, you see stuff in U other than P, different from P. Right, that's what that says. no matter how small a neighborhood you want to look in, there is something in the set U which is within that delta neighborhood of P, but 0 is less than the absolute value of x minus P, so that x isn't actually the same point as P. So if you have such a point, we'll call it an accumulation point or a limit point. If you like, we'll call it a limit point because those are the types of points where it makes sense to talk about limits. We'll call it an accumulation point because there's stuff in U that accumulates really close to P. How does everything feel right now? Pretty okay? Right, that's a definition. If you look at a point that's a point in U that is not a limit point, well then, let's negate that definition. If you look at a point that's not a limit point, then there exists some delta neighborhood such that there does not exist any x values which satisfy this inequality. So if you look at a point that's not a limit point, there's some delta neighborhood which doesn't contain anything in U other than maybe the point P itself, which is in U by assumption. So that point feels pretty isolated, right? It's got no neighbors. We'll call such a point an isolated point. We'll call a point an isolated point. A point in U, which is not an accumulation point of U, is called an isolated point. And if we quantify that, we'll call P isolated if there exists some positive number delta such that for all x values in U, either x is equal to P or the absolute value of x minus P is bigger than or equal to delta. How does everyone feel about that? Does that seem believable that that's what you would get if you negated the definition of a limit point? Yeah. And these quantifiers will be important in a few of the theorems we'll state today. Well, how about a definition, another definition? There's another idea related to the limit of a function, namely continuity. If I tell you a function is continuous at some point P, what does that mean? No, that's differential. Well, it should mean that, like, if you take an x value that's close to P, then f of x should be close to f of P. Well, that sounds a lot like the definition of the limit, right? That was like if you take an x value close to P, then f of x should be close to L. The only difference is L is now f of P. So here's the definition. So let's let U be a subset of R, and f be a function. Let P be a point in U. We'll say that f is continuous at P if, for every epsilon bigger than 0, there exists a delta bigger than 0, such that for every x in U, if the absolute value of x minus P is less than delta, then absolute value of f of x minus f of P is less than epsilon. So you'll notice there's no 0 is less than there. And let's just think about what difference that would make. What's the only x value that has absolute value of x minus P not greater than 0? P itself. So that's the only difference. This if statement is allowing x is equal to P. When x is equal to P, is this inequality true?
If it's continuous, like if there's no like dots like they're outside of P, like in that.
Yeah, this is the definition of continuous. But let's see. Forget anything about continuity. If x is equal to P, then is f of x equal to f of P? Yeah, if f is actually a function. Maybe you have something that's like not a function, in which case why are you talking about continuity of this non-function? The answer there is you need to do something else if you want to talk about continuity of like relations or something. Which you could do, but we won't. So f of x is just equal to f of p. So what's f of x minus f of p? Is that less than epsilon? Because epsilon is by assumption bigger than 0. So you could put a 0 as less than there, is what I'm saying. You will neither gain nor lose anything. I'll just say that a function is continuous on a set if it's like continuous at every point in the set. That seems like a good thing to call continuous on that set, right? So we'll just call the function continuous if for every p in U, f is continuous at p. Or maybe said a different way, for every p in U, for every epsilon bigger than 0, there exists a delta bigger than 0, such that for every x in U, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p is less than epsilon. So these two lines are literally the exact same. All I've done is expand the definition of f is continuous at p. How do people feel so far? Pretty okay? So this packet feels pretty heavy, but that's because I accidentally forgot to hit the two-sided button. So let's maybe do a quick sanity check by just seeing if something that we know is continuous should be continuous. There's a function, f of x equals to 3x minus 2. Does that seem like the type of function that ought to be continuous? Mm-hmm. Would you guys like to show it's continuous at a single value or just show it's continuous? How do people want to do the problem as written? Okay, I'll do the problem as written. If you want to just show it's continuous, then I guess you have to add some extra quantifiers in your proof. Namely, a step where you consider any p in the domain. So let's show that this thing is continuous at x equal to 1. So, all right, the definition of continuity starts with a for all epsilon bigger than 0, so what should be the first line of our proof? Consider any epsilon bigger than 0. So let's consider any epsilon bigger than 0. The next bit in the definition is there exists some delta bigger than 0. So what should be the next line in my proof?
Let delta be blah.
Let delta be blah. And let's see, so it's for all epsilon bigger than 0, there exists a delta such that for every x in the domain of the function, something happens. So it should be the next line.
Consider any x in the real numbers.
Consider any x in the real numbers, because the real numbers are the domain of this function. What do I get to assume about this real number x? There's an if-then, right? What is the hypothesis in that if-then?
The absolute value of x minus p, which is 1 in this case, is less than epsilon.
Assume that the absolute value of x minus p, and p is 1, is less than delta. Did you say delta or epsilon?
I think I said epsilon.
Doesn't matter. The one that you get to pick. And now we need to show something about the absolute value of f of x minus f of p. But we have a specific value for this function. So let's see what we can do. Then, absolute value of f of x, which is 3x minus 2, minus f of p, 3p, 3 times 1 minus 2, is equal to, and then we need to simplify that out. Maybe we get something involving x minus p explicitly. So, proceed, simplify.
For delta.
No, just for that once you simplify it as much as you can.
I know it in terms of p, so.
Okay. What did you get in terms of x's and p's?
3 times the absolute value of x minus p.
3 times the absolute value of x minus p, but I guess my p is 1. So you're proving something better. You're just proving it's continuous everywhere, I guess. Okay, so I got 3 times x minus 1, or x minus p. But what did I assume about the absolute value of x minus 1? Was there a choice for delta I could make, for which that would be epsilon? So let's let delta be epsilon over 3. This is now equal to 3 epsilon over 3, which is just epsilon. Is that exactly what I needed? Yes, let's just, well, summarize what this shows. So this shows that no matter what choice of epsilon you have, there exists a delta, namely that same epsilon divided by 3, such that no matter what x is, if the absolute value of x minus 1 or x minus p is less than delta, then f of x minus f of 1 is less than epsilon. So 3x minus 2 is continuous at p equal to 1. Nice. Does that feel pretty good about that? Yeah. So let's just, so the next goal I have, which I'll make it through, is the following. So no one gave me this definition when I asked what the definition of continuity is. There's this other idea that says that a function is continuous at a point p if f of p is the same as the limit as x approaches p of f of x. You guys remember that idea from calculus? Right, like a function is continuous if you can evaluate that function by checking the limit, or either you can evaluate the limit by evaluating the function at the point. This theorem will say that that is the case. A function is continuous at a point p if and only if the limit as x approaches p of f of x is the same as f of t. But that's not true unless you look at the right sort of points. If you're checking for continuity at a point, that point is better actually be in the domain. Otherwise, you can't plug in that point to the function, so you can't check for continuity. And that point better also be an accumulation point of a function. Otherwise, you're going to have trouble figuring out what the limit is because the limit will be like everything. But as long as you do that, we're okay. So let's just remind ourselves, the only place you should talk about limits is at accumulation. I'm going to try to stick with one word, accumulation point or limit point. And I'll try to stick with that throughout the course of the notes. How many people prefer the word limit point? How many people have a preference to accumulation point? Okay, so the vote was 2 to 1 for limit point, I think. So I'll try to say limit point from now on instead. So we can ask about limits of a function at limit points. We can ask about continuity at points in the domain. As long as both of those are satisfied, limits and continuity capture the same information. If you have let u be a subset of R, let f be a function defined on u, let p be a point in u, which is also a limit point of u, then this function is continuous at p. If and only if the limit as x approaches p of f of x is equal to f of t. This is what we'll prove, and this will take up, I think, most of the rest of the time. So we need to prove an if and only if statement. How do you prove if and only ifs? Prove one implies the other, and the other implies the one. So we have two proofs we need to do. I guess most are better declare variables that u be a subset of R, f be defined on u, p be a point in u, and p be an accumulation or a limit point. And so we have like two implications we need to do. Let's do the forward direction first, because why not? Let's show that if this function is continuous at p, then that limit statement holds. So let's assume f is continuous at p, and then I need to prove something about the limit. So that means that for every epsilon bigger than 0, I need to prove something is true. So I better consider any epsilon bigger than 0. Then I need to come up with a choice for delta. Right, is for every epsilon bigger than 0, there exists a delta bigger than 0. I don't have an explicit formula for f. I don't hope to get an explicit formula for delta. But I know a fact about f, right? I know this function is continuous. So if I pick an epsilon that's positive, and I know this function is continuous, what does that tell me? It tells me that there exists some delta bigger than 0, such that what happens? Let's see. So I think it satisfies that for every x in U, if the absolute value of x minus p is less than delta, then the absolute value of f of x minus f of p, parentheses, absolute value, is less than epsilon. Right, that's what continuity tells me. Cool, so now I have a choice of delta to work with. So for any epsilon bigger than 0, I just made a choice for delta, which hopefully is a good choice from the point of view of limits. I think it will be. But now let's go back to the limit proof. So I need to show that for every epsilon bigger than 0, there exists a delta bigger than 0, such that for every x in U, so I'm going to consider any x in U. So if you like it, this point, this is where I picked my delta. And I need to assume something about this delta. What's the assumption that I make about this x? What's the assumption I get to make about x if I'm proving something about a limit? Looks like that, right? So what is it that I get to assume about x?
0 is less than the absolute value of x minus p, which is less than delta.
Yeah. So I'll consider any x in U, such that 0 is less than the absolute value of x minus p, is less than delta. But wait, does that actually give me the assumption in this if then? So in particular, then 0 is less, nope, absolute value of x minus p is less than delta. Aha! So this pink if then I have that hypothesis. Since I have the hypothesis of this if then I get the conclusion. So maybe I'll even put like a star there. By star, we get to conclude that the absolute value of f of x minus f of p is less than epsilon. So let's just see if we've actually done it. Did we start by considering any epsilon bigger than 0? We did. Did we come up with a delta? Yeah, not an explicit one, but that's the best we could do. Did we then consider any x in the domain? Did we assume that 0 is less than the absolute value of x minus p is less than delta? Did we conclude that the absolute value of f of x minus f of p is less than epsilon? Okay. We just made a limit proof. We had just proven that the limit is x approaches p of f of x is equal to f of p. Do you think the other direction will be pretty similar? Yeah. It'll be more complicated by just a little bit, because you'll notice that in this step right here, we actually just forgot some information. So the reverse direction, we'll need to gain some information. Yeah.
What does it say in blue on the far left?
Picked delta.
Okay.
So there's a step in any epsilon delta proof where you need to pick a delta.
Mm-hmm.
That's what happened there.
Okay.
Nice. So I've been doing a lot of gesturing here, which will make it like a really bad YouTube video when I post it. So doing the other direction, let's prove the opposite. So let's suppose that the limit as x approaches p of f of x is equal to f of p. And now I want to prove something about continuity. So continuity, even its statement, is a lot like a limit. So I'll need to start by considering any epsilon bigger than 0. And then I'll need to come up with a choice of delta. But this limit statement gives me a choice of delta, doesn't it? By that assumption, the assumption that f of x approaches f of p as x approaches p, we get that there exists a positive number delta such that for all x in U, if 0 is less than the absolute value of x minus p is less than delta, then the absolute value of f of x minus whatever the limit is, but we hope that the limit is f of p. No, we assume that the limit is f of p. Absolute value of f of x minus whatever the limit is, f of p, is less than epsilon. And we need to assume something for continuity. So we're going to consider any x in the domain U and assume that the absolute value of x minus p is less than delta. And let's see, if there were 0 is less than, then we could just use this pink if then and be done with it, right? So I guess there are two cases. Either there is that 0 is less than, in which case we're basically done already. So either 0 is less than the absolute value of x minus p is less than delta, or so if we know that, let's see, so what happens if this is not true? What's the only x value for which the absolute value of x minus p is not less than 0? Not greater than 0.
X is equal to p.
When x is equal to p. And let's just see if we can do the job in each of these cases. So if 0 is less than the absolute value of x minus p is less than delta, maybe I'll call that pink line hurt this time. Then we see that by hurt, absolute value of f of x minus f of p is less than epsilon. So we're done. At least if we know that this is true. So there's another case left, the case that x is equal to p. In the case that x is equal to p, then what can you tell me about the absolute value of f of x minus f of p?
0.
It's 0, because that's f of p minus f of p. Is 0 less than epsilon? Yes. Cool. So does that complete the proof of continuity? Yeah. Because, all right, what did we do? We considered any epsilon bigger than 0. We came up with a choice of delta. So here's the step where we picked a delta. We considered any x in U and assumed that absolute value of x minus p is less than delta. And in either of the two cases we ended up with, we concluded that the absolute value of f of x minus f of p is less than epsilon. Thus, for every epsilon bigger than 0, we conclude there exists a delta, such that if the absolute value of x minus p is less than delta, then absolute value of f of x minus f of p is less than epsilon, which is exactly what we need to conclude with the continuity statement. How'd that prove you? It seemed pretty natural. And I mean, it should have, right? The statements of continuity and limits are so very similar that how could they not be related? But there was this hypothesis that you should only look at limit points in the domain for this to happen. But not every point in the domain is a limit point. There are isolated points. And isolated points are like silly, because if you look at an isolated point, then like the if part of the if then in the limit statement is automatically true, as long as delta is small enough. So the limit is equal to everything, which is bad. So you just don't talk about limits. But you can talk about continuity at isolated points. This proposition says that it's also silly to talk about continuity at isolated points because everything is continuous. So, proposition, let U be a subset of R and f be a function defined on U. Suppose that P is an isolated point in U, then f is continuous then. So let's try to prove it. Let's consider any epsilon bigger than 0, and we need to come up with the choice of delta. Now, since this point P is an isolated point, what does that give us?
There exists a delta greater than 0, such that for all x in U, either x equals p or the absolute value of x minus pi p is greater than or equal to delta.
Greater than or equal to or greater than?
Greater than or equal to.
Okay. So, there's a choice of delta. Let's see if that choice of delta is the choice we want. Let's consider any x in the domain U, and assume that the absolute value of x minus p is less than delta. Let's see, if the absolute value of x minus p is less than delta, then could this possibly be true? No, it's like exactly the opposite. But one of those two things is true, right? So what can we conclude? It must be that, I was just throwing away too far. X must be equal to p. Let's see, so maybe I'll put another sentence here. Since absolute value of x minus p is greater than or equal to delta is false, it must be that, oh, and it even works out pretty well spacing-wise. X is equal to p. But if x is equal to p, then what can you tell me about the absolute value of the difference between f of x and f of p? It's 0. Is 0 less than epsilon? Yeah. So at an isolated point, everything is continuous, because there are no neighbors to check for continuity. So you just shouldn't even ask about continuity at isolated points, because you don't gain anything by asking. So let's see, with a few minutes left, I think I'll state a few results and maybe prove just one little thing. So let's let U be a subset of R, P be a limit point of U. If you like accumulation points, leave them as accumulation points. I'll probably exit and slip up and say accumulation points on anyway. And you have some functions defined on U. Let's state some limit laws. If you have a constant function, a function that's always C, then what is the limit as x approaches P of that function? C. The limit of a constant function should be that constant. If f of x is the function which is always equal to x, then what should the limit as x approaches P of that function be? P. Right, so I guess that's saying when x is close to p, it follows that x is close to p. If as x approaches p, f of x approaches L, and as x approaches p, g of x approaches M, then what should the limit of the sum be? Sum of the limits. What about subtraction?
The difference in them?
The difference between the limits. What about multiplication?
The product of limits.
The product of the limits. What about the quotient, assuming you never divide by 0?
The quotient of the limits.
The quotient of the limits. And I even saw you already know how all of those proofs should go, because we did the proof by sequences. I'm pretty sure if you just replace all of the n's bigger than 0, n's by deltas that are bigger than 0, it'll just go through it. And I believe some of the homework will have you chase through those proofs. But for now, let's talk about some corollaries to this. So here are some corollaries. The constant function is continuous. The function given by f of x equal to x is continuous. If you have a continuous function and multiply it by a constant, you get a continuous function. If you add two continuous functions together, you get a continuous function. If you subtract continuous functions from each other, you get a continuous function. If you multiply them, you get a continuous function. If you take a quotient of two continuous functions and never divide by 0, then you get a continuous function. Let's prove one of those, it's a corollary, right? These are the continuity corollaries of the limit laws. Let's prove one of these by using some limit laws. Let's prove result 7. So let's suppose that U is a subset of R, P is a point in U, F and G are functions defined on U which are both continuous at P. Let's also assume that U never divide by 0. G of x is never equal to 0. We need to show that f of x divided by g of x is continuous. And I'm going to use this translation, I'm going to use this as idea that limits are the same as continuity at limit points. But not every point is a limit point. The point P might be an isolated point. But by proposition 3.1.6, what can you conclude if P is an isolated point? Yeah, well, everything is continuous, right? In particular, f of x divided by g of x is continuous, because that's a function. We see that f divided by g is continuous at P. Nice. On the other hand, if we look at an accumulation point, well, then we've assumed that f and g are both continuous at P. So by theorem 3.1.5, what can we conclude about f of P? Possibly by rereading that theorem. A function is continuous if and only if the limit as f, well, if and only if f of P is the same as the limit of f of x. And it follows also that g of P is the same as the limit as x approaches P of g of x. So what can you tell me using limit laws about the limit as x approaches P of f of x divided by g of x? Well, that should be f of P divided by g of P, right? By limit laws. Wait, did I just show that the limit as x approaches P of the function I want to show as continuous is the same as evaluating the function I want to show as continuous at P? Hey, but wait, I have this theorem that says that that's equivalent to continuity. So again, by theorem 3.1.5, f divided by g is continuous at P. Cool. Nice. So I'm over time. I hope you all had an enjoyable day. Think some about the practice problems for that midterm exam I want to give next week. Don't lose sleep about it. Think about enjoying the normal waking hours. Yes. That's exactly what you took from me a second ago. Wait. Bryce. Good thing you haven't left yet. I'm going to give you a thing back.
Oh, thank you.
Excellent.
Yeah, I was thinking about that, like, when I sit in abstract, I probably don't make any difference to you or not, but if I just turn around.
Yeah, you lost some hair.
Yeah. I might lose even more of it, but I like this better than the way it was before. I always wanted to have longer hair when I was younger, but I just never tried it. And I was like, well, you know, junior year of college, probably last time that it'd be like blanket acceptable to just have horrible hair.